I would like to conclude the concepts of the signal space uh, with comparison with vector space, and now we will solve an example as well. So we learn about the signal space and the vector space, the three-dimensional. In both of the cases, if we compare the signal space, the signal space, and here I would mention the vector space, so if I compare these two, in vector space we have three unit vectors: unit vector I, unit vector j, and unit vector k. We need these three unit vectors to define three-dimensional vector space. And here in the signal space we need three. Now keep in mind I, j and k are perpendicular to each other. Similarly, we in the signal space we have three signals which are psi 1 of t, psi 2 of t, which we represent by this notation psi 3 of t, and these three signals, or these three functions of time, these are orthogonal to each other. They are orthogonal to each other. So all the three signals are orthogonal, and we define the three-dimensional signal space. Another property is the magnitude. The magnitude here, the we know that the magnitude of unit vector I, the magnitude of unit vector j, and the magnitude of unit vector k, all is unity. Now here in the signal space we have the energy. Define the energy for the signals, that the energy of psi 1 and the energy of psi 2, and the energy of psi 3, all these energies are equal to unity. Now when we define the energies equal to unity, we call these functions, basis functions, as the orthonormal basis functions. Now they have two properties: they are orthogonal, and their energies is normalized to unity 1. Now another property which is important is their dot product. We say that the dot product of these signals, for example, the if I take I dot I, it is same as j dot j, and it is same as k dot k, and all this is unity. Here in case of signals, the dot product of psi 1 and psi 2, and we mentioned the dot product of any signals. If I say the dot product of psi 1 of t with psi 1 of t from minus infinity to plus infinity, this is the dot product of the signals. It is same as the dot product of psi 2 of t, psi 2 of t, and we say the integral dt. It is same as the dot product of psi 3 of t, psi 3 of t dt from minus infinity to plus infinity, and this dot product is unity, because we already mentioned that the energies is unity. So this will be the actually it becomes the integral of the square of the signals. It becomes the integral of the square of these signals, and the integral of the square of the signal is its energy, which we already mentioned that it is one unity. Now another property, if you see that if you want to find the image, before that let me clarify that any vector b in three-dimensional space, as we mentioned, can be written as a linear combination of these unit vectors bxi, by, j, and bzk. Right? It can be written as a linear combination of these unit vectors in three-dimensional vector space. Here in signals, what we can do, we can write any signal, a three-dimensional signal, as a linear combination of psi1 of t, psi2 of t, and psi3 of t. So we say that we can write Sm of t as a linear combination of this a times psi1 of t plus b times psi2 of t plus c times psi3 of t. So we can write these signals as a linear combination, as a signal Sm of t as a linear combination of these three basis functions. We call it the basis functions. And if we move further, we discuss it. If we go a bit more, we can discuss some more properties. We can discuss some more properties of these two. We can just compare these two further. So if I continue with the same comparison, now if you want to find the image of B, the image of vector B along x-axis, or along the direction, in the direction of the ith unit vector, I unit vector, you have to find the dot product of B with this unit vector, and it would give you the B of x, the image of, it would give you a scalar that gives you the length of the vector along the, or actually the length of the vector along along the direction of I, or in the x-axis, in the direction of x-axis, or I would say the image. It gives me the measure of the image, image of vector, the vector B, which is similar to the ith unit vector. It is the measure of this similarity. So in the same way, we discuss for signals that, okay, we have three-dimensional signal Sm of t, and if we find its dot product with psi1 of t, from minus infinity to plus infinity, this would give me the component of Sm of t along psi1, which I have mentioned above, a. So let's write a specifically. So it would give me a. It's the component of the signal, Sm of t along psi1 direction, or we say the image of Sm of t over psi1, the image of Sm of t over psi1 of t. Okay, we define these, we can find out these signals. Now vector B can be, vector B in three-dimensional can be represented as a point, a signal, one point, and you have three components for this one: bx, by, and bz. So this is a, you can say that it's position vector. in three-dimensional plane. You have x, you have y, and you have z. Similarly, we can define our signal in three-dimensional plane, and we can say, okay, we have three-dimensional signal space, and we have psi 1 here, psi 2, okay, and psi 3. And this is a three-dimensional signal space. And any point here defines a signal point A, B, and C. This is the signal point and a signal vector. This is vector B, right? Here it is vector B, and this position vector represent the vector S, which is signal vector. So the signal can be seen as vector in the signal space, and this is a signal point. Now extending this concept to extending the same concept. Now if I plot a two-dimensional, now if we have two-dimensional, three-dimensional is the space, we call it the signal space, but most of the time usually we deal with the vector. If the vectors in two-dimensional are easy, and they are easy to manipulate, and you are already familiar with it, okay, you have this signal in these two-dimensional signals, right? Two-dimensional vectors. So you have vectors here, a vector here, a vector here, a vector here. Now we can define for two-dimensional, we say the Euclidean space, two-dimensional vector space. Instead of using the term plane, I would like to use the term space, right? So psi 1 of t and psi 2 of t are the two basis functions. Now I can define the signal points here, and these are my signal points because each of these points will have two components along psi 1 and along psi 2. It would be a linear combination, and these vectors, position vectors, they represent the signal vectors. So we have this signal space. We define the signal space. Later on you will see that this diagram, actually this diagram is for signal points, which is supported in the 4G of wireless communication. But I leave that discussion for later lectures. So let me give you an example now. If you let me give you an example of this signal space. Suppose